All right, let's get started. Sign-in sheet. Get that passed around. Okay, so not very many new announcements. Homework 6 is still being graded. Homework 7 due on Monday. Remember, no late submissions because we are doing our exam review on Monday, and then we're going to have our exam 2 on Wednesday. Now that we're talking, or now I'm sitting here, I do have one other announcement. You all got an email yesterday from a firm looking for some material testers. Did you all see that? So if you're interested, send them a resume. I know you know how to test concrete cylinders, or at least a vast chunk of you, because I'll do what I can. Okay, like schedule conflicts.
Yeah, so like the real question is, are you going to have like advising sessions?
I'm going to work on it.
I'm not going to name names, but the guy that's teaching our geotech class is my advisor. And he's not going to advise us.
I'll work on it. So what you're saying is, I will work on it. I'll work on it. Okay. All right. Let's get started. What we're going to do today. All right, everybody, settle down. All right, so what we're going to do today is we're going to continue our discussion of immediate deflections or instantaneous deflections. Again, that means the same thing. And then we'll start to discuss long-term effects. So let me sort of recap just to, really quickly get everybody back into that mindset of what it is we're talking about. Remember, I want everybody to be absolutely clear about this. You cannot compute live load deflections directly in reinforced concrete design. If that was a little fuzzy last time, it's definitely going to make a little more sense today when we finish our 15A example. So you always compute the dead load deflection first, then the deflection due to all of your load, your dead load plus live load, and your live load deflection is the difference. And the reason why you cannot compute the live load directly is because from here to here, from dead to dead plus live, your moment increases, so you have a different moment of inertia. If you have a different moment of inertia, your deflection changes, and it's not as one-to-one. Let's sort of recap our example, and then once we finish this and go into and get into this math a little bit, I think this will become a little more prevalent. So remember, we are looking at 15A. We've got to compute the instantaneous deflection, which for right now is just the regular old deflection, everything that you all learned last semester in structural analysis. That will become clear, the difference between instantaneous and long-term effects today. Now we've got this beam. It's 20 foot long. It's simply supported. Whoop, about fell over on that bookcase or book bag. I will remember that. All right, so think if I had fallen over, where would you learn reinforced concrete design?
This is a safety issue here.
Yeah. All right. He does have my back. he demonstrated that last semester. Okay, all right. So we've got the instantaneous live load deflection on this beam. It's 3 KSI normal weight concrete. It's 20 foot long. We got 1 kip per foot in dead load, and then 0.7 kips per foot in live load. Now the beam's 20 inches wide by 12 inches wide by 20 inches tall. It has a 17-inch effective depth, and then there's 3 number 9s in it. Now let me just recap the calculations that we did on Monday. Okay, so here we've got the calculations that we did on Monday. We've got our parameters. And remember, there are 3 quantities that we're going to compute throughout a deflection computation that are going to remain fixed. There's the gross moment of inertia, these are the 3 quantities that I have written up here because we're going to refer to these quite a bit. We have our gross moment of inertia. That's just BH cubed over 12 for a rectangle. If you've got a T-beam or something like that, you got to break out your parallel axis theorem and what have you. But for this, pretty straightforward. It's just 8,000 inches to the 4th. Now, we've got our cracking moment. FRIG over YT, we plug and chug. That ends up being about 27.4 foot kips. That's relevant because we're going to use that in our effective moment of inertia calc. Plus, it gives us a little bit of a visual cue as to what's going on. when we start looking at our applied moments and we see that they're larger than this, we know that some of the beam is cracked and some of it isn't. So that gives us a little bit of a visual cue. Now the one that takes a little bit of work is the cracked moment of inertia, or our transformed moment of inertia. So remember, there's a few steps that you got to go through to do that. So you got to compute your modular ratio. Remember, E sub S over E sub C. E sub S is always 29,000. E sub C, 57,000 square root of FC prime for normal weight concrete. And you take the integer value of that. So we just take N to be equal to 9. Now, for our location of our neutral axis, remember we turn that steel into an effective lump of concrete through the use of that modular ratio. And then we're basically doing sum of AY over sum of A, basically just summing moments of area to determine that neutral axis. So we ended up getting a neutral axis of X is about 6.78 inches. And then use our parallel axis theorem, I plus AD squared, to get the cracked moment of inertia. When that was all said and done, that was about 4,067 inches to the fourth. So did anybody have any questions on that? That actually wasn't really deflection material. That stuff we did a while back in January, but everybody should be pretty familiar with that. Sound good? Okay, all right. So this was the new stuff. So we've got our three quantities that don't change: our gross moment of inertia, our cracked moment of inertia, and our cracking moment. And then remember, we take these load cases one at a time. So what we did last time was we did the dead load. So our dead load is 1 kip per foot. So our applied moment, our N sub A, is WL squared over 8. So that came out to 50 foot kips. So if I look at my moment diagram, I've got my cracking moment that's 27.4, but the maximum moment at midspan is 50. So right off the bat, you can see that some of the beam is cracked and some of it isn't, right? So when we compute our effective moment of inertia, it's not going to be 8,000. It's not going to be 4067. It's going to be somewhere in between. And we got 4714.2 inches to the fourth, right? Remember, don't forget to cube these terms in parentheses. That's an easy mistake to make on the computation side. Then we compute our deflection. That's just regular old structural analysis that we did last semester. 5WL to the fourth over 384 EI. Plug and chug. Don't forget unit conversions, because we got feet and inches all over the place. So remember, your deflection unit conversion is 1728. Pop quiz, what's your rotation conversion? Anybody remember that? Ooh. It's 180 over pi, but there's something else. 180 over pi is the radians to degrees, but if it's 1728 for deflections, what's the other number for rotations? There we go. Remember there's an L squared in there for rotations, and there's an L cubed in there for deflections. So, okay, so when it's all said and done, we got a dead load deflection of about 1/4 of an inch. It was about 0.245 inches. Everybody okay with that? Now, here's, if all this, inability to compute live load deflection directly didn't make sense before, I think right now this is going to clear all this up. Okay, so watch this. Let's look at dead plus live. So this is the deflection due to dead plus live load applied at the same time. So our dead load is 1 kip per foot. What's the live load? Somebody remind me. 0.7, is that what you said? Okay, so help me out. How do I compute the applied moment? How do I do that? WL squared over 8, but it's not just WD or WL, we're adding both of them. So it's going to be WD plus WL L squared over 8. Did I forget my load factors? No, I didn't. We do not apply load factors at the service limit states. So no 1.2 and 1.6 here. You just add them up directly. So this is going to be 1.7 kips per foot. I'll just go ahead and add that up right now, times 20 feet squared divided by 8, And plug and chug, what does that come out to be? $85 foot kips. Do I have a second on that? Okay. Now, I want everybody to put their thinking caps on for this one. Look what happened here. Our applied moment is 85 foot kips. Is that larger than it was for just dead load? Yeah. We only had 50 foot kips a moment for dead load, but when we threw the live load on there, we got a little bit more. What is that going to do? You don't have to worry about trying to interpret the equation. Just use your noggins here. What is that going to do to our moment of inertia? Is our moment of inertia going to get bigger or smaller? No. Think about this. Let me ask it a different way. Has the beam experienced more cracking under the dead plus live? Yes. So if the beam has cracked more under the application of additional load, is the moment of inertia going to increase or decrease? It's going to go down, right? So let's test that theory. Let's see if that happens. So our effective moment of inertia is MCR over MA to the third times IG plus 1 minus that. All times our cracked moment of inertia. So notice how if you look up top on the screen, the only thing that changes is MA. All these other three equations are, all the other three parameters are constant. So 27.4 foot kips divided by 85 foot kips times 8,000 inches to the fourth plus 1 minus, what did I forget? Cube, there you go, see? Divided by 85, and then that's cubed times, what was it? There we go, making sure everybody's paying attention. Okay, and what does this come out to be? $4198.8 or 7? 4198.7 inches to the fourth. Do I have a second on that? Take your time. Okay. Everybody good? Now, there are two checks as to whether or not that number makes sense. Okay? First off, somebody tell me why this number makes sense when you look at these two. It's between them, right? The effective moment of inertia has always got to be somewhere between the gross moment of inertia and the cracked moment of inertia, the two polar extremes. So we got 8,000 and 4067. This is 4198. So we know that that makes sense from some standpoint there. Okay, now what's another reason it makes sense? We compare it with these two. It should be less, right? We threw more load on the beam. So because we threw more load on the beam, more of the beam has cracked, so the moment of inertia goes down. Okay? And this right here, this is the main reason why you cannot compute live load deflection directly. Because in order to compute the live load deflection directly, the moment of inertia has to stay the same. It doesn't stay the same. Because when you throw more and more load on a reinforced concrete beam, more of it cracks, so the moment of inertia goes down. So you have to handle each case separately and just take the difference. Does that make sense? Everybody okay with that? Okay. Yes, sir?
I don't think I'm understanding why there's more cracking when inertia.
Because take a look at this. All right, so here's our moment diagram, right? And it looks something like this, right? Sound good? Yeah. Okay, all right. Now I'm going to draw two moment diagrams. I'm going to draw one here, and I'm going to draw one here. And I'm going to exaggerate it a bit just to make sure everything makes sense. Now, let's say this moment diagram is due to just the dead load. So the top of this is at 50, right? Okay? So 27.4, the cracking moment might be here and here. So 27.4, 27.4. So I would say that only this much of the beam right here is the part that experiences cracking. Sound good? Now, let's look at our dead plus live. This is 85, right? So 27.4 on this diagram might be like down here or down here. So that means that much more of the beam has cracked. Does that make sense?
Yeah.
So that's basically it. So if under dead load, the beam effectively looks like this. Under dead plus live, oh goodness, I don't know what happened there. It looks like that. More of the beam has experienced cracking, so its overall stiffness has gone down. Does that make sense? Everybody okay with that? Okay, so the one thing left to compute is our deflection. Now this is the deflection due to dead plus live. So that's going to be 5, not WD, WD plus WL times L to the 4th over 384 EI. Now that's E for the concrete, and I is our effective moment of inertia. Okay, so let me see if I can squeeze this in here. So 5 times 1.7 kips per foot times 20 foot to the 4th over 384. What's EC? Maybe I ought to write that up here on the board. What was EC? Go ahead and have that there because we'll refer to that here in a sec. So that's 3122 KSI. And then what did we say? 4198.7 inches to the 4th. Now what am I forgetting? So up here up top I need a 1728 inches cubed per foot cubed. So what am I getting for this? We got a number? Bless you. 0.467. What are the units? This is deflection. Yeah, it's inches. Do I have a second on that value? Okay. Now again, the main reason why we can't compute live load deflection directly, right here, different moments of inertia. If we could use the same moment of inertia, I'd just use live load, I'd just use 0.7 kips per foot and just calculate it directly and move on. But because the moment of inertia changes, you can't compute live load deflection directly. Everybody good on this? Am I good to go on to the next panel? So I'm only going on to the next panel because I just cannot fit it over here, but we really don't, we only have one minor calc left, so continued. So, let's see, well, how did I do that? So if I just look at live load deflection, it's pretty simple. So we have the dead plus the live, and that was 0.467 inches. Remind me, what was this? So what is the live load deflection going to be? There you go. So and what is that? Second? Any questions? That's not bad, right? I'm going to show you here in a sec where we're going to use that, but for now I want to make sure everybody's clear so far as to where that value is coming from. Everybody good?
So if you want like
Yeah.
the total deflection, you would use the D plus the L, right?
Yeah.
No.
If you're wanting to know like how much it's deflecting overall, yeah, it would be 0.467. Normally we don't really care about that though because we can camber the beam to account for the dead load deflection. So we can camber the beam up like 1/4 of an inch.
Oh, okay. So
And then
you're just worried about the line.
you're only worried about the live because under its own self-weight, you can fabricate the beam such that it will sit flat. So what we're more interested in is under live load, meaning us, how much of that's going to deflect. Does that make sense? Any other questions? This is good stuff. Yes, sir.
How realistic is it to camber the beam for like 0.245 inches?
That's a great question. 0.245, honestly, probably not. It's probably not that much. 1/4 of an inch, we probably would ignore. It depends on the magnitudes. Usually, if you're hitting that like 3/4 inch range or something like that, we'll probably do something. And usually in concrete land, we'll just prop the formwork up a little bit. In steel land, we will actually bend the beam upwards, like actually feed it through a horizontal, cold bend it to where it's actually curved upward a little bit. We can take care of that in concrete design through just propping the forms up a little bit. But if we're talking like 1/4 of an inches over a beam that's 20 foot long, it would probably be conventional to ignore it. That's a good question. So it just depends on your magnitudes. Now, for instance, in bridges, good luck trying to get that, 1/4. If you're looking at like an 80, 90 foot long bridge and you've got a 1/4 inch dead load deflection, that is a beam. That is a that is a really deep. Well, it's the truth.
Do you have to pre-bend the rebar for that as well?
No, but that's a good question. We typically usually don't worry about that. I mean, one thing to point out, if you're propping up your formwork and your rebar is sitting on chairs inside the formwork, then it's going to kind of lay. I mean, how many of you have ever like picked up just rebar by itself? It's got about as much stiffness as a piece of wet spaghetti. It just, so it can form. That's pretty easy. So that's a good point. But no. Now, we are going to talk here later on about development length and how you actually do bend rebar into hook shapes for development purposes. But that's a little bit later. That's exam 3 stuff. So we'll get there. So far, so good? Okay, let's talk a little bit about long-term effects. Okay, and then the deflection limits are going to show up here in a second because I know some of you are probably like, well, great, it deflects 0.222 inches. Who cares? And what does that matter? Well, in order to discuss that, we really kind of need to talk about the difference between immediate deflection and long-term deflection. And what I mean by that is what we just did is what are the deflections immediately after the load is placed on there, or instantaneously right after the load is placed. In other words, here's the beam, put the load on there, what's the deflection? Okay, so we got 0.222. Now my next question is, well, what happens if we take that load and leave it on there for 5 years, 10 years, what have you? Well, under the effects of time, concrete properties change, okay? Concrete will undergo shrinkage effects, creep, there's differences in humidity, temperature effects, so on and so forth, and that changes the properties of concrete and the behavior of concrete over time. So the long and short of it is the deflection that you get on a reinforced concrete beam today is not the same deflection that you'll get on that beam 5 years from now if that load remains consistent. So we have to account for that. Now, one of the things that's going to show up here in a second is a term called rho prime. Okay. Now, remind me, we used rhos to represent what when we were doing beam designs? Like, what was rho? It was the reinforcement ratio, right? Remember, rho was AS over BD, right? It was basically how much steel you got versus how much concrete you've got. Well, what you're about to see here in a second is rho prime. Now, when we throw a prime on any of those dimensions, what does that represent? Compression steel, right? So that's the steel up top. So if you start going through the literature and start looking at all the laboratory tests and whatnot that's been done on reinforced concrete beams, you'll find that a lot of tests have shown that having compression steel in the beam actually improves a beam's long-term deflection performance. It sort of contains those regions in compression over time. So you can actually get a little bit of a benefit on your long-term deflection performance if you have compression steel in the beam. And that's going to kind of rear its head here in a second when we look at example 15b, but let's sort of take it one step at a time. Okay? One question that we have to ask, and I know students usually sometimes get a little frustrated at the final answer, but we have to ask how much live load is sustained over an element's design life. And a really nice example of that is looking at this classroom. Okay? When we first started discussing loads in this class, you know, we agree that the load in here is different than, say, the load in a warehouse or a library or something like that. Like, remember how we said the library load is about 150 pounds per square foot? That's because there's book stacks all over the place, and they are very, very heavy, right? Well, that's absolutely the case. But one other question we have to ask is about how much of that load is sustained. I would argue that for a storage facility, a warehouse, a library, something like that, I would argue anywhere from 80, 90 to maybe even 100% of that design load can be assumed to be sustained over its design life. And what I mean by that is that load is always there. I mean, granted, college students check out books every now and then, although nowadays we're checking out books on our iPads and whatnot. I've got some engineering students like, we don't read. We're engineers. There's more laughter at that joke than there should be. I'm just saying. But in all seriousness, it's fair to say that in a storage facility type situation, it's a safe assumption that most of that load is always going to be there. That probably isn't a reasonable assumption for this classroom, okay? Because think about this. This classroom is designed for, I think what we said, like 50 pounds per square foot. But are there any students in here at 2 o'clock in the morning? I hope not. They got all this homework. What is always in this room that is related to occupancy? What is always in this room? The tables, the chairs, the desks, and so on and so forth. The students aren't always in here, but the equipment and what the room is being used for is. So maybe from a design standpoint or from a deflection standpoint, we've got 50 pounds per square foot, but maybe only 20% of it, maybe only 30% of it is sustained, is always there, okay? So one of the things we'll have to ask is not just how much live load is on the system, but how much of that load is sustained throughout its design life. And I know where students get frustrated, they're like, well, where do I look that up? Where's that value? There really isn't a place to look that up. You got to just use your judgment, okay? It depends on what you're looking at. It depends on if you're designing floor beams for a library versus an office building versus so on and so forth. It boils down to what the structure is being used for, and you're using your noggin. So there are, I mean, obviously if you're working at a firm that does nothing but hospital design, they're probably going to have a value that they use across the board. But if you got a new project, got to use your noggin a bit. Yes, sir?
How does that change for bridge, where it's not really, you don't have a sustained load?
That's a great question. That's a great question. So the question was, how does this change for bridges? And the answer is the bridge code offers far more prescriptive means for assessing live load deflection. It specifically defines what load case you are to check when assessing live load deflection, and it specifically spells out your limits. So fortunately for bridges, deflection isn't really something that you have to guess at. It's not really something that that as a bridge engineer you got to guess, well, what load am I going to consider? The code specifically spells that out. So you don't, there's not as much of a judgment standpoint, but it's the nature of the beast when it comes to buildings, because bridges are really only used for one thing, to carry vehicular traffic. I mean, you got pedestrian bridges and whatnot, but that's it. Buildings are used for offices and hospitals and schools and all this different stuff. So that's where judgment comes into play. I'll get back to that. I actually will get back, discuss something related to that later on in the semester, but all I'll say is this: that bridge was a unique one. It was unique. It was a very complex system. It was pre-stressed. And that's a whole different ball of wax. So, yeah, that's a whole other thing. Yeah.
So which of these two scenarios you have on the board, which one will have the better chance of getting to its design life becoming faster? The one that's always at 100% of its load, or the one that fluctuates?
That's not really the question that we would ask. It's really more about this. It's more about once you have ascertained, so you're trying to figure out like which one will better reach its design life. It's really more about based on the structure you've got and based on the sustained load that it's going to see, the question is how big does that beam need to be in order to meet that design life? Does that make sense? So I'm sort of asking the opposite question. And that's what most structural engineers are going to consider is what's the opposite question. So does that make sense? Okay. Now, here's how we assess long-term deflections. Okay? We take our immediate deflections and we then adjust them through a modification factor. Now the modification factor is this term here that's in parentheses. It's this term xi divided by the following quantity. Now, it's a Greek letter. Don't. Guys. A great many structural engineers see this symbol and just draw squiggles. It's okay. It's a happy little bush. It's a happy little tree. All right. What? It looks like the dragon from Mulan? Now that's a first. All right, barring the Disney representations of our time-dependent factor, this is actually a really easy computation to make. I want everybody to pay attention. So you take your immediate deflections and you then adjust them by what's in here, and you really only need two adjustments. You need two quantities. You need a time-dependent factor, which I'm going to show you how to get that here in a second. And you need a reinforcement ratio for compression steel. Remember rho prime, that's our BD on the bottom, and on the top it's not the area of steel, it's the area of steel in compression. So if you have no compression steel, then this term is taken to be 0, and your adjustment is just this factor. So is everybody okay with that? Everybody good? Okay. Now how do you get this factor? It's basically off of this chart. This comes straight out of the ACI code. I've got a few interpolated values here. We typically look this up and look up, we'll just about drop this. We look up our value and report it to the nearest tenth. So if you're looking at 24 months, so if you've got a sustained load that's going to be on there for 24 months, let's draw this here. I don't know, maybe like 1.7, 1.6, something like that. So just interpret that the best that you can. No, yes. Give me it'll be clear. Give me 1 sec. All right. So that also, let me supplement that answer a little bit. That comes again from engineering judgment. So for instance, if you're talking about a classroom scenario, if we agree that in here maybe 20% of that load is sustained, it's also a function of is that load going to be there all the time forever, or is it only going to be there for a certain period of time? Like for instance, if we're talking about a classroom, maybe that load is only sustained for a period of 9 months, because after 9 months they come in here and they clean the room out or what have you. That again also boils down to judgment and a specific application. If you don't know, I might just say forever and just take the maximum quantity, which would be 2. Does that make sense? It just depends on the application. So.
Let's say they did take everything out in like 9 months because it started over. Like how long would it have to be gone before they bring it all back in?
That's a good question. I mean, you take load off of a beam, it's going to respond pretty quickly. It's going to respond back up. I would always say that when in doubt, just be conservative, but it also depends on what you know. and it depends on the application. Again, for a classroom, it might make sense to use something like 9 months or a year or something like that if the room's going to get rearranged or if there's going to be, tables taken out or so on and so forth. So.
So like say 9 months actually goes through you classroom, you got
Mm-hmm.
then the next year, say it gets brought back up 3 months later. Does it just start over?
Yeah, is basically what I'm saying. It's throughout its design life, how much of that load is sustained and what's a typical period for it to be sustained. Is it forever? Is it a year? It just depends on the application. So, does that sound good? Now, one thing we do have to discuss is we have to discuss the limits, okay? Because right now, what we're talking about is, up until now, all we've said is, okay, great, we have a deflection of 0.222 inches. What the heck do we do with it, okay? So let's take a look at this first and make sure that we're clear on this. There are, at most, 5 deflections that we can compute. We have our dead loads, we have our dead plus live, then we have our live load, which would just take the difference, right? Now, likewise, we have our live load, our dead load deflection, and dead load plus live, we have dead load plus sustained live load deflection, right? So to get the sustained live load deflection, it's just the same thing. Take your difference. Does that make sense? Okay, but what we have to do is adjust them. Now watch this. To get our total deflection, the absolute total deflection in the beam, here's what we're going to do. We're going to take our instantaneous live load deflection and we're going to adjust it by 2 quantities. The first thing that we're going to do is we're going to adjust it by our dead load deflection that has been modified for time. Now, look at this. Look at my time duration factor. So I might have sustained load that's on there for 9 months, but my dead load is on there forever. My dead load doesn't go anywhere. Like the self-weight of the beam is there always. So when I adjust my dead load deflections, look at my time dependent factor. I'm always using a value of 2. Why am I using 2? Because that's sort of my ceiling on that graph, and that dead loads are always there forever, okay? Whereas for my live loads, it depends on the duration. If it's there forever, use 2. If not, use what makes sense, okay? So we have instantaneous deflections, and then we have total deflections. We then compare those deflections against our specified limits. So here's our limits. When we assess deflections, we have to make sure that we are assessing deflections according to appropriate limits. So we've got really 4 different types of members that we're going to assess, and I want to read these one at a time. So let's take the first one. Okay, actually, well, let's take the first 2 because they're going to be very similar. Okay, so the type of members. So the first one says flat roofs not supporting or attached to non-structural elements that are likely to be damaged. Okay, whereas the second one says floors not supporting attached to structural elements that are likely to be damaged. And if you look at your deflection limits, here we have L over 180 versus L over 360. So we take the span length and we divide it by either 180 or 360 to assess our immediate or instantaneous deflection. Depending upon the likelihood of damage, that element can get, the deflection limit can get a little more stringent. Like take these. Roof or floor construction supporting or attached to elements that are likely to be damaged. Roof or floor construction supporting or attached to non-structural elements not likely to be damaged. So if the member that you're checking is supporting, like let's say it's a hospital or something, and let's say it's a floor beam in a hospital that's supporting, I don't know, the MRI machine, okay? You might have a little bit more of a stringent deflection check on that, because if that beam deflects too much, that might throw the MRI out of calibration, and then that creates issues. So that beam might have to be bigger and might have to be stronger. Doesn't have anything to do with its safety or its strength, but it's because of its use. If that beam is supporting, a complex or a highly calibrated MRI machine, that may be a little bit of an issue. Okay? Does that make sense? So what I'm going to do, just to illustrate what's going on here, I want to look at example 15B, and I want to assess its deflection requirements, and I want to assess its deflection requirements based on the fact that we're going to say that this is a floor beam that is likely to be damaged by deflections. And then in addition, we're going to consider that 30% of this load is sustained, and we're going to say it's sustained over a period of 3 years. Okay? And I'm doing this because I want you to have a little bit of experience interpreting this graph, and I want you to understand what these deflection computations mean. Okay? And I think you're going to find this is really not that difficult. You just got to make sure that you're interpreting things appropriately and that you understand what's going on. Now, before we get into this example, what is rho prime? What's that? It's 0. It's the reinforcement ratio for compression steel. What's the deal? There is no compression steel. There's no steel up here. So because there's no steel up here, rho prime is 0. Okay? So I want everybody to be paying attention to that. So if you try and take this and divide it by BD to get a rho, that's wrong. Okay? There's no compression steel, so this is 0. Sound good? Okay. All right. So let's sort of play around with this and let's see what's going on. And I want to show you another thing with this particular example. I want you to see how the deflection computations can be quite regular and quite repetitive. And if you can understand that, I mean, once you understand how to do deflection computations once, you can do them over and over again because they're, like I said, they're pretty repetitive. So let's look at this. Let's look at example 15b. Okay. Now, let's look at our parameters. All right. I want to look at these parameters because I want to have all of this, I want to have all this data up here up top. So let's start off with our loads. So we have a dead load of 1 kip per foot, and we have a live load of 0.7 kip per foot. Now, help me out. What is our sustained live load going to be? So we'll say, for instance, that this is a class, or let's say it's an office building. Let's say it's a conference room in an office building or something. So what's our sustained live load for this problem? Anybody remember? 30%. So we're going to say 30% of WL, and what is that? What is 30% of this? 0.21 kip per foot. Is everybody okay with that? All right. How long is this beam? 20 feet. Okay. Now, we've got E sub C is 3122 KSI. And then I'm going to write my 3 other quantities. We've got the cracking moment, which is 27.4 foot kips. We've got IG, which is 8,000 inches to the 4th. Excuse me. And our crack moment of inertia, 4067. Okay. Now, I'm going to repeat some computations, but I think you'll see why. Okay, deflections. So I'm going to draw myself a little table down here. Okay, so we're going to do our case. And I propose we've got 3 cases of deflection that we're going to compute directly. We're going to have our dead load plus our live load, and our dead load plus our sustained live load. All right? Now, the first thing I want to report is I want to report what is our applied load. So, watch this. For the dead load case, I propose that the only load that we have applied is 1 kip per foot. Everybody okay with that? How about for dead plus live? What's that? 1.7. How about for dead plus sustained live? Okay? Now, if I have each of those loads, how can I then compute the moment? What do I do with each of those loads? How about WL squared over 8? So if L is 20 feet, what do I get 1 times 20 squared over 8? Doesn't this come out to be, oh, I don't know, 50? All right? What does this second one come out to be? Anybody remember? 85. This is 85. So what's the third one? Not too bad, right? Taking each of those, I can then compute an effective moment of inertia. So help me out. Anybody remember what this one was? $47.14.2, and this one was what? It was like 4198.7. Now, how did you compute these? Well, you took MCR over MA to the third times IG plus, so on and so forth, right? So do the next one. Right? Here, I'll go ahead and write it out for you because I'm nice. What I'm getting at is, isn't this a nice, friendly Excel template just begging to be generated? Once you do one, just copy and paste. You can do them all over. So what are we getting here? Anybody got an answer? $44.32.4. Do I have a second on that? Do I have a second on that? Okay, all right. So if you've got that, you can compute your deflection in inches. And how do you get that deflection? Well, you take 5W L to the fourth over 384 EI. But then don't forget your conversion factor of. All right, so what are you getting for each of these? It's a trick question. You shouldn't have to do the first two. 0.245 inches, and this one is, this is inches to the fourth, inches to the fourth. So what are we getting for the next one? While we're at it, I can put over here on the side that the live load deflection is the dead plus the live minus the dead, and that came out to be 0.222, and then the sustained live is going to be the dead plus the sustained live minus the dead, and we'll see what that is here in a second. So what are we getting for this one? 315. Do I have a second on that? So if we know that, what's our sustained live load deflection? So we'll say 0.070. All right. Before we call it for the day, is everybody okay with this? Now that you've done deflection calcs once, isn't this a lot faster? A lot more straightforward. You know, once you do it once, the calculation should get real repetitive. Like you should get real familiar with calculating an effective moment of inertia and ultimately calculating a deflection. Now, before everybody leaves, one thing to remember. This blue formula and this green formula, they only work when you have a simply supported beam and you have a uniformly distributed load. Whenever your loading or your geometry or your boundary conditions change, these formulas stop working. So I don't want you to get lost in, well, that's the formula we use. You got to make sure that your structural analysis is being performed appropriately, all right? That's all I got. See you on Friday.
Why do we have to do that?
You know. Hold on. You know the answer to that.